This talk is about the simulation of the effect of targeted simulation on the peak number of infections in complex networks. My name is Michael Emmerich and I'm Associate Professor from the Leiden Institute of Advanced Computer Science, and this is joint work with Yulian Kuryliak and Dmytro Dosyn from the Lviv National Polytechnical University in Ukraine. I will give a brief introduction on epidemiological models on complex networks and then show our simulation environments using continuous time Markov chains and Gillespie algorithm for efficient simulation of epidemic outbreaks. Then we will discuss targeted immunization and centrality measures and show our results on the dropping of the peak number of infections in epidemic outbreaks and a new idea for visualization of infection routes, which are the contributions of this paper, and followed by a small conclusion. Let us look at the problem first. Targeted immunization of a network deals with the problem of finding nodes that we need to quarantine when we have an epidemic outbreak, like in the COVID-19 situation. We had a spread of the virus through a social network of contacts between people, for instance, here symbolized by a map of a country and how the different cities are connected. And the question is which nodes to immunize in the network with priority to prevent the spread of the disease. In our modeling, we focus on individuals, not on cities, but it's a small difference. So the contacts between individuals are the links. There would be two strategies to consider, and we compare them in our paper. The naive strategy, the simple strategy, is big nodes first. So nodes that have a lot of contacts should be immunized first. The second strategy would be to look a bit deeper into the importance of a node in the connectivity of the entire network, and this leads to the notion of eigenvalue centrality and shortest path centrality, as we will see. There are different networks dynamics in the compartmental model of epidemiology. The SI dynamics, susceptible nodes can become infected, stay infected, and infectious. SIS dynamics, susceptible nodes become infected, and then they recover and are susceptible again, so they can reinfect, like in the flu epidemic. And SIR dynamics, which is similar to the COVID-19 epidemic, susceptible nodes can become infected, then they recover, and after recovery they are immune, at least for a longer time. And then we can simulate this by means of continuous time Markov chain models that are realistic in the treatment of time. And in a previous paper series we have described our efficient simulation of such models on realistic network topologies. And this leads to results like we see here in the right-hand side plot. We can simulate the outbreak of the disease multiple times by the stochastic simulation algorithm. And we see where the epidemic reaches its peak, the highest number of infected nodes can be determined, which is the focus of this study. We want to reduce the peak. And we also can find visualizations of the process of getting the network infected, of the invasion of the virus. So this is a new suggestion in our current MoMLeT paper, where we propose to use color and width of the edges to visualize the outbreak of the disease. So there can be many ideas how to do this, but this summarizes multiple simulations. They are stochastic, so each simulation gives a slightly different trajectory, and we can see likely routes. Targeted immunization. The main topic of this paper focuses on the idea of node centrality. So which nodes we should quarantine with priority if we can only quarantine a limited number of nodes. So we would like to have a criteria how important a node is for the network. Traditional, we focus on the local effect. We look how many contacts a node has. So big nodes are immunized first. Here, however, we consider also systemic centrality metrics that look at the entire network and the role of the node in the entire network connectivity. And this, we can say, is a global effect of a node, because not only direct neighbors are considered. To motivate the importance from a common sense point of view, think of a bridge node that connects two clusters or two communities. This bridge node might not only have two contacts, so it's not a large number of contacts, but it is very important for the virus to spread from one big community to the other big community. So by removing this node or quarantining this node, it would be impossible for the virus to infect a large part of the network. And how can we measure in a coherent measure this systemic centrality? So in the literature has been proposed the maximum eigenvalue of the adjacency matrix for the SIS dynamics, or the maximum eigenvalue of the Hashimoto non-backtracking matrix for the SIR dynamics. The Hashimoto non-backtracking matrix is sketched here. I will not go into the details, but it's basically a matrix that is formed from a network of adjacent edges. So when you have one edge in the original network and another edge following, there can be a link between these two edges, and we exclude backtracking edges. So if this edge leads to the original nodes back, we exclude it from this matrix. And it has been motivated by message parsing and then recently applied in the epidemiology studies in network science. Why are these eigenvalues important? The maximum eigenvalue is inversely proportional to the epidemic threshold. What is the epidemic threshold? Well, if the contagiousness of the virus is above the epidemic threshold, the virus will invade the entire network. So we have to make the epidemic threshold as big as possible, and that means we have to remove large eigenvalues from the network, nodes that have large eigenvalues associated. However, in this study of this MoMLeT paper, we focus on the reduction of the peak number of infections and not on the increase of the epidemic threshold so much. So we might consider other centrality metrics as well. For instance, the average shortest path length that turned out to be a good metric in a previous paper. Results. Well, I show results for removing 5 nodes as an example of how important it is to use the right network models and also the right centrality measures. Here we see Erdos-Reni models, which assumes that each node has about the same number of contacts, and there it does not so much matter which centrality metric you use. So the big nodes, node first strategy works best, and works not best, but can be slightly improved by using eigenvalue centrality. But for realistic, for social network topologies models, like the Barabasi scale-free model, which has a realistic degree distribution, or the small world network represented by the Watts-Strogatz model, it is indeed important to choose the right centrality measures, and it leads to significant and substantial reductions of the peak as compared to the naive strategy of just focusing on the biggest nodes first strategies. So we see here that EAM and ENBM, so the non-backtracking matrix and the adjacency matrix eigenvalue strategy, has a 40% lower peak than the highest degree strategy for targeted immunization. So this is one of the key messages of this paper. Focus on the wide centrality matrix that considers the entire network, and the difference between adjacency matrix and non-backtracking matrix seems to be not so significant, but you get a slight difference also here. This is about the reduction of the peak, and we have obtained this by simulations. We do multiple simulations and make statistical summary of these simulations for different sizes of networks, and our results are summarized in tables that confirm the major trends that it's much better to focus on systemic centrality measures in the immunization than on the simple highest degree strategy. The other matrix that we might want to consider for the epidemic counteracting epidemics would be the vulnerability of the network to the invasion of the virus. So sometimes the virus is not even able to invade the network, so this is indeed related to the epidemic threshold. And we see here that the differences between highest degree strategies and network-based strategies are less strong, and the eigenvalue-based strategies perform indeed best, which is also what theory predicts. Conclusions: we have shown that immunization strategies can be tested on network models by means of realistic continuous time Markov chain simulation and also efficient simulation. And we challenge the state of the art in multiple findings. So we see that simulation can be done efficiently. In previous papers we have shown linear versus exponential time using the naive approach. And then we have seen that when you focus on the peak number of infections, this can be supported by our simulations, and different to the R number that is the main focus in classical studies. The network topology indeed matters, and we focus on scale-free small world networks, which are much more realistic than assuming that all nodes have about the same number of contacts. So the choice of the centrality measure matters in these topologies, and we recommend to use eigenvalue centrality instead of biggest degree first removal strategies. This leads to a much better drop of the peak, and also we can consider the right type of matrix for computing the eigenvalues. The non-backtracking matrix is, from a theoretical point of view, preferred for the SIR pandemic, but for other diseases it might be the adjacency matrix, depending on the dynamics. And we also showed that there can be new ideas of visualization based on stochastic simulations. We can visualize the likelihood of certain paths in the networks for causing the infection. Thank you for your attention.